Welcome to the DMV Math Circle's Polynomial Irreducibility workshop. And I'm just going to be going over some basics and some criteria, and we're going to be doing some problems. So before we begin, I would like to thank Arnav for sending me the LaTeX source code of his number theory workshop from last year for a reference. And if you're interested, be sure to go to the DMV Math Circle YouTube channel to access all our prior workshops. All right, so here's an introduction. Polynomial irreducibility is important in both algebra and number theory, and Olympiads as well as higher math. And so since this topic occasionally appears in Olympiads, make sure to master it. This workshop's gonna go over its basic definition, some irreducibility criteria, a lemma, and some problems. And at the end, like all of our other workshops, there's going to be some resources for further study. And a PDF download of this presentation along with a recording will also be available in our Discord server. And for this specific workshop, I decided to create a handout with two proofs of the two criteria I'm going to be proving today, and also include two walkthroughs for the proofs of the other two criteria so that you can try to prove them yourselves. What is polynomial irreducibility? We call a polynomial irreducible if it can't be factored into non-trivial polynomials. So that means they aren't that the two polynomials that it can be factored into have to be itself over some given ring. And it's kind of similar to prime numbers because for prime numbers, they can only be factored into one in themselves. And for polynomials, they can only be factored into one in themselves or negative one and the negative version of themselves. And when we say that a polynomial is irreducible, we have to specify the ring we're working with. Because, for example, the polynomial x squared plus 1 is irreducible over the polynomial rings in C, Q, and R because its roots are complex. But then that means that this polynomial is reducible over Cx because it can be factored as x plus I and x minus I. And another interesting factorization for this polynomial is over the polynomial ring in F2 because x plus 1 squared is equal to x squared plus 2x plus 1, and then taking that mod 2 would make it the original polynomial. So that means we must specify the ring we're working with. And in this workshop, we're going to be mainly working with Zx as well as Qx. Two important concepts in irreducibility are content and primitivity. The content of a polynomial is just the greatest common divisor of its coefficients, so it's just the GCD of A0, A1, all the way to AN. And this is important because it directly relates to primitivity, because a polynomial is primitive if the content is equal to 1. And so in many contexts, we have to require a polynomial to be primitive before proving that it's irreducible, because if it weren't primitive, we could always factor out the GCD of the coefficients in Zx and Qx. So for example, even though x squared plus 1 is irreducible in Z and Q, 6x squared plus 6 can be factored as 6 times that irreducible polynomial. So um, that's just kind of like a trivial factorization that we must not include in the problem. The first criterion we're going to be going over is Eisenstein's criterion, and it states that if we have this polynomial f of x, if there exists a prime p such that p divides every coefficient except the leading coefficient, and p squared does not divide a0, then f must be irreducible over z. And this final condition kind of just means that since p divides a0, that means the highest power of p and a0 must be 1. So we're going to be proving this first. Wait, does anyone have any questions? Wait, we're fine, right? Right, thanks. So, we're gonna be proving this first. And yeah, so here's do you see my screen? The whiteboard? Right, thanks. So we're gonna be proving this. And in a lot of irreducibility proofs, we first, for the sake of contradiction, assume that the polynomial f of x is reducible. So we assume that f of x can be written as g of x times h of x for non-trivial polynomials g of x and h of x. So we require the degree of g and h to be less than n, which is the degree of f. And assume that g of x is equal to bk times x to the k plus bk minus 1, x to the k minus 1, all the way to b0. And we assume that h of x, we just write it as cl x to the l plus cl minus 1, x to the l minus 1, plus dot 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 plus c0. So, it's kind of hard to see where to start, but we haven't addressed the conditions, the divisibility conditions in the criterion. So we first do that. The second and third are clearly the easiest ones to address. So if you look at the second one, P doesn't divide AN. If we expand this, if we expand G of X times H of X and set it equal to this polynomial here, we can see clearly that AN is equal to BK times C of L. And also since F is equal to G times H,
Yeah.
note the degree of F, which is N, is equal to K plus L. And so since AN is equal to BK times CL, and P doesn't divide AN, that means that P must not divide either of BK or CL. And for this condition over here, along with the fact that P divides A0, that means, so P divides A0 and P doesn't divide, P squared doesn't divide A0. Along with the fact that A0 is just equal to B0 times C0, that means one of B0 and C0 has to be a multiple of P, and the other one can't be a multiple of P. So without loss of generality, we can just assume that P divides B0 while P doesn't divide C0. And now with these conditions, we can move on to a stronger claim. And so right now we claim that P divides B1, B2, all the way to BK minus 1. And so first to do this, again, similar to AN and A0, we write expressions for A1 all the way to AK minus 1. So basically, for A1, we have A1 equals to B1 times C0 plus B0 times C1. And similarly, we have A2 is equal to B2 C0 plus B1 C1 plus B0 C2. And all the way to AK minus 1 is equal to B k minus 1 times C0 plus bk minus 2 times C1 all the way to B0 ck minus 1. And so this is true because we can just expand g of x times h of x and match the coefficients of each, and noting that k plus l is just n. And with this, we can start an inductive argument. So the base case is that P divides B1. So we prove this using this first equation over here, because from the criterion we have P divides A1, right? So for this first equation over here, if we take this mod p, a1 is just 0 because p divides a1. And then we don't know anything about b1 times c0 yet, so we just write it down. And then for b0 times c1, from the above argument, we already have p divides b0. So p must divide b0 times c1. So just plus 0 mod p. And so that just means p divides b1 times c0. However, since we already know that p does not divide c0, this implies that p must divide b1 in order for it to divide b1 times c0. And similarly for a2, since p divides b1, this expression is just 0, and p divides b0 implies that this expression is also 0. And p divides a2 implies that this is also 0. So that means p divides b2 c0. And again, since p cannot divide c0, you have p divides b2. And I'm not gonna write out the whole inductive argument and like the hypotheses and stuff, but we can easily see that going down the list, for A1, we can conclude that P divides B1. For A2, we can conclude that P divides B2. So that means for AI, for the equation for AI with I is greater than or equal to 1, less than or equal to K minus 1, we have P divides BI. So this is just our claim because if I ranges from 1 to K minus 1, we have already proven that P divides B1, B2, all the way to BK minus 1. And we can more rigorously prove this using induction, but it's kind of easy to see if we write it out. And now with this argument, we can write a similar equation for AK because we've only written equations for A1 all the way to AK minus 1. We haven't used any of AK all the way to AN yet. But we only need AK because AK equal to BK C0 plus BK minus 1 C1 plus dot 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 plus B0 CK. If we have, because since K is less than N, because we said that this is a non-trivial factorization, so that means K must be less than N. So since K is less than N, we must have P divides AK, because we know that P divides A0 all the way to AN minus 1. And since K is less than N, it must be one of these. So if we take this equation mod P, we get the left-hand side is just 0 because P divides AK. And BK times C0, we can't do anything about that yet. And for the rest, we have BK minus 1 times C1. We know that P divides BK minus 1. So that means this is just 0, and then the rest of it is all 0. Wait, and I'm going to check what I got so far. Yeah, I'm also going to be posting this handout. And, right. So, however, in the beginning, we already know that P cannot divide BK, nor CL. So for this final expression, we write it on the side, P cannot divide BK. And also from here, we're using this for like the kth time already. P cannot divide C0. So yeah. But however, from this equivalence, we have P divides BK times C0. Which is a contradiction because this implies that one of BK and C0 must be a multiple of P. However, in the beginning, we already established that P cannot divide any of them. So with this contradiction, that means our original assumption that f can be written as g times h is wrong. So therefore, f cannot be reducible, so f is irreducible. And we're done with the proof. And yeah, it's Eisenstein's. But if you have any questions, just type it out in chat. All right, so if not, we're gonna be moving on to the proof for, we're gonna be moving on to the example for Eisenstein's criterion. So we know that this is true because we've already proved it. So I wrote this example. It's pretty simple, but it's just an direct application of Eisenstein's. So we want to prove that x to the fifth plus 10x squared plus 5 is irreducible over c. And so if we look at the conditions, we need to find a prime p. Well, if we see the coefficients 10 and 5, it's kind of screaming at us that we want p to be equal to 5. So let's see if that works. So if p is equal to 5, then yes, the constant coefficient is a multiple of 5, and it isn't a multiple of 5 squared. So that condition is satisfied. And the other condition is that P cannot divide AN. Well, AN in this case is just 1, so that's obviously satisfied. And all the coefficients in the middle are multiples of 5 because they're 0 and 10, which are obviously multiples of 5. So this polynomial is irreducible by Eisenstein's criterion. All right, so we're going to move on to the next criterion, which is Perron's criterion. So Eisenstein's is probably the most famous by far, but Perron's is also quite famous. So if you have the polynomial f of x, note that this time the leading coefficient of f of x is 1 because we have a 1 instead of an this time. And we also have a0 is not equal to 0. Suppose that the absolute value of an minus 1 is greater than the sum of all the absolute values of all the other coefficients, then f is irreducible over z. This is quite different from Eisenstein's because the other one is that we need to choose a prime that satisfies a couple of divisibility conditions regarding the coefficients, and for this one, we must have one coefficient dominates all the other coefficients in an inequality. And so the proof is going to be quite different as well. So if we look at the statement, which is right here, um, so our first claim is that all roots of f have magnitude greater than 1. So, okay, so we want to prove this claim. All right, so if we want to prove this claim, we use contradiction again. So if we assume that the roots of f are z1, z2, all the way to zn. And so if we want to prove that all these roots have magnitude greater than 1, it's kind of hard to prove that if we want to directly use all these roots. So we do this by contradiction. Assume that one of these roots has magnitude less than or equal to 1. Without loss of generality, assume that that root is z1, so that the magnitude of z1 is less than or equal to 1. Well, since z1 is a root of f of x, we know that um we know that z1 to the power of n plus, oh wait, I think I'm proving the wrong criterion. Right, so I have a walkthrough for Perron's criterion. My bad. I'm gonna be proving the next criterion. So the walkthrough for Perron's is over here. Wait, that's my bad, sorry. Well, I'm gonna be sending this PDF in the Discord server after the workshop. So we're just gonna be looking at an example and you can prove this for fun if you want after the workshop. So Perron's is very useful because we can prove some polynomials irreducible as long as their second coefficient clearly dominates all the others. So x cubed plus 4x squared plus 1 is clearly irreducible because 4 is greater than 1 plus 1. And okay, so now this is the correct criterion that I'm going to prove. So this is kind of similar to Perron's. And if we have f of x is equal to this polynomial, and this time we have the leading coefficient is an. Suppose that a0 is a prime number, and this time a0 is greater than the sum of the absolute values of the other coefficients, then f is irreducible over z. And so now we can go back to this proof over here. That was really my bad, sorry. And so if we continue what we got right here, so with a0 is a prime and the final coefficient is greater than the sum of all the others, our first claim is that all the roots of f have magnitude greater than 1, and we assume these are the roots of f. And to prove this, we use contradiction. We assume without loss of generality that one of the roots, c1, is less than or equal to 1, the magnitude of it. And since it's a root of f of x, we have an times c1 to the power of n plus an minus 1 times z1 to the power of n minus 1, all the way to a1, z1, and a0. And since z is a root of f, we have this is equal to 0. And now, if we move this a0 to the other side, I'll just copy all this real quick. Wait, okay. Whatever. I'll just write it out. an times z1 to the n plus an minus 1 z1 to the n minus 1 plus dot 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 all the way to a1 z1 is equal to negative a0. And then if we take the magnitude on both sides, so we have the magnitude of the left-hand side is equal to the magnitude of the right-hand side. Well, the magnitude of a negative number is just its positive counterpart, so it's just the absolute value of a0. And for this, let me check. All right, so this left-hand side over here, since we assume over here that z1, the magnitude of z1 is less than or equal to 1, the left-hand side over here can actually be written as um an c1 to the n. I mean, we can bound it, but we can bound it above at the sum of all the coefficients that are included here. Because if we think about it, z1 is less than or equal to 1, and this value over here must be less than or equal to the absolute values of this, plus all the way to that. And then that sum must be bounded above by this sum over here. Because z1 is less than the absolute value, the magnitude of z1 is less than or equal to 1. So this over here is just bounded above by this expression, which is, and we want this because this is just the right-hand side of the inequality in Ostrowski's criterion. And so this left-hand side over here, by the above equality, is just equal to a0. So that means this implies that a0 is less than or equal to this sum over here. However, in Ostrowski's criterion, we assume that a0 is greater than all of these. But over here, we obtain that a0 is less than or equal to the sum of all of these. So that means that's a contradiction. So we cannot have a single root z whose magnitude is less than or equal to 1. So we have proven the claim that all roots of f have magnitude greater than 1. So after this claim, so again, similar to Eisenstein's criterions proof, we assume that f of x is equal to g of x times h of x, and again for non-constant polynomials g and h. And back in the criterion statement, we have a0 is a prime number. So that means g0 without loss of generality is equal to plus or minus 1, and h0 is equal to plus or minus a0. And this is true because since f of x is equal to g of x times h of x, if we substitute x is equal to 0, we can easily obtain that a0 is equal to g of 0 times h of 0. And a0 is prime, and the values of g and h have to output integers. So that means one of them must be plus or minus 1, and the other must be the plus or minus a0. And so we can assume that g0 is equal to plus or minus 1 without loss of generality, and then let the degree of g, be equal to k, just like in Eisenstein's criterion, but this time we don't need the whole polynomial. And let the leading coefficient be bk. And now we can use Vietta's formulas, because right here, we can assume that the roots of g of x are z1 all the way to zk, because we already assumed that the roots of f are z1 all the way to zn. And since g of x is a factor of f of x, all the roots of g of x must be roots of f of x. And so we can write the roots over here. Right. So right now we can see that g0 is equal to plus or minus 1, and the roots of g0 gx are z1 all the way to zk. And now back to this, we can use Vietta's formulas to get z1 times z2 all the way to zk is equal to negative 1 to the k times g0 over b, because, or bk, because if we have some polynomial, just say bk all the way to b0, it's just the final coefficient divided by the leading coefficient, which is just by Vietta's formulas. So we write that down. And we want to look at the magnitude of this value. Well, the magnitude of this value, the negative 1 to the k just doesn't matter anymore. And since g0 is equal to plus or minus 1, this numerator over here simplifies to 1. And the denominator doesn't change, so that's equal to bk. And so, um, oh, I skipped a sentence, but we know that the magnitude of the product of all these roots is greater than 1 because of the above claim, because all the roots of f have magnitude greater than 1. So clearly the product of all of them is greater than 1. So if we have this value 1 over the magnitude of bk, we have 1 over, by Vietta's formulas, we have 1 over bk is greater than 1. However, since f of x factors into g of x times h of x, g of x and h of x, we want to factor it over z. So that means the coefficients of g and h are all integers. And so the absolute value of all their coefficients must be at least 1 or 2 or 3 dot dot dot. But however, our argument with Vietta's means that um, means that 1 over bk is greater than 1, so bk is less than 1. However, since we know that the absolute values of the coefficients must be at least 1 or 2 or 3, that implies that there's a contradiction, because by Vietta's formulas, we have this value is greater than 1, which means that bk is less than 1, which contradicts our assumption that it's factored over z. So that means f must be irreducible. And that follows a similar thought process for Perron's criterion as well. And our Zoom meeting, because I don't have premium, it's gonna end in like around, it's gonna end around like right now, so probably need to like rejoin the meeting. I'll post it in the Discord server. All right, so we left off at proving Ostrowski's criterion. So we already finished the proof, and we've established that f is irreducible as long as these conditions are satisfied. So the example problem is prove that x to the seventh plus x to the fourth plus x cubed plus 5 is irreducible over z. And so this is obviously Ostrowski's because the final coefficient is a prime number, and it also clearly dominates the other coefficients. So 5 is greater than 1 plus 1 plus 1, and 5 is prime, so this polynomial is indeed irreducible over z. And the final criterion I'm going to be going over is Cohn's criterion. And I feel like this is like far less famous than the other ones. I don't know, but I feel like other than Cohn's, I could have covered Schoenemann's criterion, but it was kind of like similar to Eisenstein's, so I included it in the end for further study. And so back to Kahn's criterion, we have let b greater than or equal to 2 be an integer, and f be this polynomial over here, with all the coefficients of f greater than or equal to 0 and less than or equal to b minus 1. And if f of b is prime, then f of x is irreducible over zx. So I'm not going to be proving this one specifically, but there is a walkthrough for it, and I'm going to be posting this handout. So this criterion is pretty useful, and it's more interesting than useful though, I would say, because this is kind of like a representation in base b, the fact that x is equal to b, and all the coefficients are less than or equal to b minus 1. It's really similar to writing a number in base b. And so the example problem for this is prove that x to the fourth plus x plus 1 is irreducible over z. And so we just got to test some values of b. So b equals 2. So note that we can't do b equals 1. That might be, yeah, we can't do b equals 1, even though x equals 1 in here just becomes 3, and it obviously works because the coefficients wouldn't be less than 1. So the next number we're going to try is b equals 2. And so if we plug in 2, we get 16 plus 4, 16 plus 2 plus 1. And so that's 19, which is clearly a prime number. And looking back at the criterion, the conditions are all satisfied. So that means f is irreducible. And in fact, another number that works is b equals 5, because 5 to the fourth is equal to 625, x is equal to 5, and plus 1, that becomes 631, and that's also prime. So yeah, this criterion is really interesting, and I just shared it because I thought it was pretty fun. And we're going to be moving on to the example problems now, the Olympiad problems. They're going to be from the IMO, Como, and the China team selection test for the IMO team. So the first problem is let f be this polynomial over here, where n is an integer, and prove that f of x cannot be expressed as the product of two non-constant polynomials with integer coefficients. And note that what we want to prove right here is just that f of x is irreducible over z. And this polynomial over here, we have one coefficient clearly dominating all the other ones because it's 5 and it's 1 and 3. So 5 is clearly like the largest coefficient by far. And so that means we should immediately think of Perron's and Ostrowski's criteria. Well, in this case, we're going to be using Perron's criterion because 5 is the second coefficient over here. So that's just 5 is greater than 1 plus 3, 5 is greater than 4. That's clearly true, so we have f is irreducible over z. So this problem was quite straightforward, but I'm pretty sure in the 1993 IMO, I don't think Perron's was accepted because it was in 1993, but nowadays Perron's is probably going to be accepted in Olympiads. Yeah. Yeah, there was also like a proof. There was also a proof using Eisenstein's, and this was intended in the contest because Eisenstein's was accepted in the contest, I think, because it was much more famous at the time. Well, I'm pretty sure Perrin's is okay now. But this is like, um, yeah, this is like clearly trivial to Perrin's. So, yeah. All right. So the next problem is going to be using Eisenstein's though. So, it's algebra problem 429 from Cohn, and it was from 2007. Find all pairs f of x and g of x of polynomials with integer coefficients such that f of g of x is equal to x to the power of 2007 plus 2x plus 1. Well, this is kind of like hard to start. It kind of looks like a functional equation, but you can't really do anything to it. And so that's why we're inspired to use calculus and like a tiny bit of calculus in the beginning where we take the derivative on both sides. And so the left-hand side is just the chain rule, and the right-hand side becomes 2007, x to the 2006, and then plus 2. This is much easier to tackle because on the left-hand side we have two clear factors. And on the right-hand side, it's irreducible by Eisenstein's because with the prime number 2, it doesn't divide 2007, but it divides 0 and 2, and 2 squared clearly doesn't divide the constant coefficient, which is 2. So again, since this right-hand side is irreducible, it must, if we have to factor it in order for the left-hand side to be kind of solvable, the factors have to be plus or minus 1 and plus or minus of this expression. And now we proceed with casework. And the rest of this problem isn't really related to irreducibility, but it's definitely really good for practice with polynomials and stuff. So the first case is that the derivative of f and then g of x is equal to plus or minus 1. Well, that means the other factor has to be what's on the screen right here. And so if we integrate both sides, we get g of x is equal to this value plus k for some constant k. And then the original equation, if we plug this value for g of x back into the original equation, since f is a polynomial, clearly f is linear and the leading coefficient is 1, so or plus or minus 1. So f of x can be written as plus or minus x plus c for some constant c. And we want to solve for k, so we can write all of it in terms of c. Write the original equation. If we plug in g of x again, and we have, oops, and we have the expression for f of x as well, we get the left-hand side is just x to the power of 2007 plus 2x plus or minus k plus c is equal to um, whatever's on the right-hand side right here. And so we get k is equal to minus plus c plus or minus 1. And this notation over here, I'm just assuming that the two possible pairs are negative c plus 1 and positive c minus 1. So like the order of like the plus and minuses are actually matter. So in this case, if we substitute k back into this expression for g, we get this solution pair. And now for the case that the derivative of g is equal to plus or minus 1, we can just integrate both sides. Like the previous case, we get that g is just plus or minus x plus c. And then plugging that back into the original equation is just this value over here. And then we substitute x with plus or minus x minus c. Because if we do plus or minus x minus c for x, it just becomes f of x. And the right-hand side is this value over here. So in this case, we have f of x is equal to this value. And going back to the previous slide, we have, again, g of x is equal to plus or minus x plus g. And we're done with this problem because we already found the two solutions. And so they're over here. And these solutions are true. I mean, these solutions satisfy the original functional equation for any constant c. And the final problem, that was on Olympiad, which is the China TST 2008 Quiz 6, Problem 2. Thanks for Alexi for giving me this problem as a suggestion. So here it goes. Let n greater than or equal to 2 be an integer. Prove that there exist non-zero integers a1, a2, all the way to an, such that the polynomial f of x right here, note that it has leading coefficient of 1, is irreducible over the integers. But the absolute value of f of x is not prime, aka it's composite for any integer x. All right, so this is more of a construction problem than actually proving some polynomial is irreducible or like some functional equation. So, um, we kind of construct different polynomials for separate degrees. So for degrees n is equal to 2 and 3, we directly construct examples, and for n equals to 4 or above, we construct a general example that utilizes the degree. So first we tackle n is equal to 2 and 3, and we can do that using similar ideas. So we construct irreducible polynomials that only obtain even values that aren't equal to 2, because that guarantees that f of x, the absolute value of f of x, isn't prime, because obviously any even number can be factored into 2 times some other number as long as it isn't the prime 2 itself. And note that we can easily check for irreducibility just by testing rational roots, because that's really easy for lower degree polynomials. And for n equals 2, we have the construction x squared plus x plus 4. And it obviously only obtains even values, because if x is even, then the whole thing is even. If x is odd, then this value is odd, is even, and then plus an even, it's even. And this function also doesn't output 2, because if we set it equal to 2, we have x squared plus x plus 2 equals 0. And there aren't any integer solutions for that. So it can't output 2. And obviously it's irreducible because if you try to factor it, the solutions are irrational. And for n is equal to 3, oh wait, for this one, the solutions are complex. And for n is equal to 3, we have the function x cubed plus 2x squared plus x plus 6. That works because, again, we can do casework on x's parity, and we can also set it equal to 2 and make sure there aren't any integer roots. And I'm just checking chat right now. All right, so continuing, this is also clearly irreducible because we try to find any roots using the rational root theorem. It must be either 2, 3, plus or minus 2, plus or minus 3, plus or minus 1, dot, dot, dot. So, yeah, it doesn't work. So it's irreducible. Now, where we actually use Eisenstein's criterion is when n is greater than or equal to 4, because in this case, we can create a general polynomial, and note that this polynomial does not work for n is equal to 2 or 3, because it depends on this final part. And if n was 2 or 3, this final part is constant, so it doesn't work. So if we look at this polynomial, if we pick any odd prime number p, this satisfies Eisenstein's criterion, so it's irreducible. And so we only need to care about the other condition, that all output values of f of x, absolute value, is not prime. So we can ensure that it only outputs composite numbers by forcing f of x to be congruent to 0 mod 4 because if any output is a multiple of 4, it's clearly composite. And so for if we add the extra condition, P is congruent to 3 mod 4, if we just do it by casework on the residue of x mod 4, we can see that indeed f of x only outputs multiples of 4. And so f of x is never a prime number, so we have constructed a function for n is greater than or equal to 4 as well. And one final tiny tweak is that the existence of p is trivial because clearly the prime number 7 satisfies 3 mod 4. So yeah, we can construct an infinite family for this problem. And so we're done with the Olympiad problems. And I'm just going to go back to an important lemma because I decided to go through these problems first because they were all regarding polynomials over Zx. But this lemma is pretty important as well as intuitive because it kind of implies that if a polynomial is irreducible over Zx, then it's irreducible over Qx. And also the converse is true. It's Gauss's lemma for irreducibility. And it's exactly what I just said. But Gauss's lemma is like a general concept in field theory and abstract algebra, but it can be a corollary for irreducibility. I mean, a corollary of Gauss's lemma is for irreducibility. And so I feel like this is really interesting. You can find the proof online. It's really easy to find it online. But we didn't need it for any of the problems we did today, but it's just really interesting because it's also really intuitive and logical. And finally, for further studying, I provided 4 links over here. You can click into each of them in the slideshow that I'm going to be posting in the Discord server. So they're going to be going over Schonmann's criterion, extended Eisenstein's, a handout, and also Newton polygons, which is essential for irreducibility. And one final trick that Arnav suggested that I should show is a trick that's mainly used for Eisenstein's criterion. I'm gonna stop sharing for now and share my whiteboard. Hold up. Yeah, so one final trick, I think it's really important in irreducibility. So, a very famous example for Eisenstein's criterion is that any polynomial of the form x to the p minus 1 over x minus 1, which is just x to the p minus 1 plus x to the p minus 2 dot 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 all the way to 1 is irreducible over Z for any prime number p. And so this is a really famous example that was found by Gauss, I think, but obviously, Eisenstein's criterion can't be directly applied to this polynomial because it's a binary polynomial where all the coefficients are 1. So, but what we can do is that we can make a substitution for x because note that if a polynomial f of x is irreducible over z, then it's equivalent to the polynomial f of x plus 1 being irreducible over z, as well as any f of x plus n for an integer n, right? So for this example, that was kind of an application of Eisenstein's criterion. The correct substitution was f of x plus 1. And using the binomial theorem and stuff, we can come up with a function that has coefficients that are divisible by p, with the final coefficient not being divisible by p squared and the leading coefficient not being divisible by p. So yeah. So we can expand this to make sure. Hold up. So for the first one, we have x to the p minus 1 plus p choose 1. Oh, wait. My bad. Okay, wait. Never mind. I addressed the problem in chat. So yeah, you can try this yourselves and substitute x plus 1. But oh yeah, in general, like this, like, do you mean by like in general that this might not work every time or something? Yeah, all right. Yeah, so yeah, so just remember that these substitutions might not work, like especially if we have like a really large polynomial or something. If it doesn't work for f of x, doesn't mean it's gonna work for f of x plus n. But this is just worth trying, especially in like Olympiads and stuff. Yeah. All right. So this is just like a really cool trick to prove polynomials irreducible if the original polynomial isn't like easily proven to be irreducible by a criterion. All right. So yeah, so if you want to study polynomial irreducibility more, just go through these links. They're pretty cool. And thank you everyone for coming and stay tuned to the DMV Math Circle, like the Discord server and Instagram, everything, YouTube channel for future workshops. And we're also gonna host more events in this coming school year. And so as far as we know, in terms of workshops, there are gonna be two more this school year, and there's probably gonna be more than two, because so far we know two people want to do workshops. So yeah, thanks for coming everyone, and stay tuned to the DMV Math Circle. And I'm also gonna be posting this handout in the server as well. Thanks everyone. And also thanks for DMV for giving me this opportunity to present a workshop. See ya.